Hi, this is Mr. Higley, and we're doing Chapter 11, Section 1. Our objectives here in this session are to define pressure, give units of pressure and describe how it's measured, state the standard conditions of temperature and pressure, and convert units of pressure from one set of units to another, and then use Dalton's law of partial pressures to calculate partial pressures and total pressures. You'll understand all of this a little bit later. First thing we're going to do, though, you'll notice up at the top here it says Chapter 10. We're going to review a little bit about the kinetic molecular theory of matter, which we need for this section. This is in Chapter 10, Section 1, and so if you need any additional information, you might go, and I would actually strongly recommend that you go there and read that. Okay, the kinetic molecular theory is based on the idea that particles of matter are always in motion. And you've heard me say that. All matter is made of particles that are in constant motion. And we can use this theory to explain properties of solids, liquids, and gases in terms of the energies of the particles and the forces that interact between them. An ideal gas is a hypothetical gas that perfectly fits all the assumptions of the kinetic molecular theory. Now, in actual fact, most gases are not ideal gases. However, under the correct conditions, and you'll see that here in a minute, under the right conditions, they behave pretty much like ideal gases. And so this ideal gas idea is not just pie in the sky stuff. Many gases do behave under most conditions in similar manners. It's based on the following 5 assumptions. The first one is that gases consist of large numbers of small particles that are far apart compared to their size. This means that most of the volume of a gas is empty space. So when you're looking out in the air in front of you, the majority of that of the air is empty space. Only a small portion of it is actually taken up by the molecules that are in the air, by the nitrogen and the oxygen and carbon dioxide and water vapor. That makes up only a small portion of the total volume of the air. Collisions between gas particles and between particles in the container walls are elastic collisions, and what this means is that no energy is lost. So as the particles bounce off of the walls, they don't lose any energy. Now, if you think about if you were to take any kind of a ball, a baseball or a basketball, and throw it against the wall, it's not going to come back to you at the same speed. Many of you have done this in the gym. You take a basketball, you stand maybe 10 feet away from the ball, from the wall, and you throw the ball against the wall, and the ball slows down and comes back at you, but it bounces once before it gets back because it's not going as fast as it was when you first threw it against the wall. Some of the energy is lost in the collision with the wall. However, in an ideal gas, no kinetic energy is lost. In a gas, the particles are in continuous, random, rapid motion. So each particle has kinetic energy. Then there are no forces of attraction between the gas particles. In other words, 2 gas particles, when they get near each other, do not have a tendency to attract each other. Now, this is one of the places where, with a real gas, we find some differences between the ideal gas and a real gas, because most gas particles do have some attraction for each other. However, that is usually relatively small, especially when compared to the energies of the particles. Finally, the temperature of the gas depends on the average kinetic energy of the particles of the gas. Now, we actually define temperature as a measure of the average kinetic energy of the particles in a substance. So when you measure the temperature of anything, you're actually measuring the average kinetic energy. And so there's a very, very close relationship between kinetic energy and temperature. You're familiar with the idea that as we heat up a gas, or any substance for that matter, the particles begin moving more rapidly. And so a gas at a higher temperature, the particles simply have more kinetic energy. The kinetic energy is given by the equation Ke equals 1/2 mv squared. So you can see that the kinetic energy of any particle depends upon its mass and the square of its velocity. Now this has some implications for gases. First of all gases at the same temperature are going to have the same average kinetic energy, because we just said that temperature is a measure of the average kinetic energy of the particles. What that means is that if you have two samples of two different gases at the same temperature, the gas that's composed of lighter particles will have higher average speeds than the heavier gas particles, because they have smaller masses, so they have to have a higher speed to make up for that, to have the same kinetic energy. Okay, remember our equation, Ke equals 1/2 mv squared. So if the mass is less, the velocity has to be higher to make up for that. So lighter gas particles will be moving faster than heavier gas particles. Those of you that were here in my class before break, you remember that little demonstration, that animation I had, and it actually showed that the lighter particles are moving more rapidly. What this tells us then is that hydrogen molecules will have a higher speed than oxygen molecules if they're both at the same temperature.
The kinetic molecular theory describes the behavior of gas molecules and the physical properties of gases. The kinetic molecular theory views gases as being made up of large numbers of fast-moving particles that are far apart from each other. Most of the volume occupied by a gas is empty space. Gas particles are in continuous rapid random motion, and the forces of attraction or repulsion between them are essentially non-existent. Kinetic molecular theory relates the kinetic energy of gas particles to the temperature of the gas. Gases differ from solids and liquids in that they expand to fill the shape of their container. Because there are large distances between gas molecules, gases have extremely low densities. Carbon dioxide, for example, is less dense than water, so bubbles of carbon dioxide rise to the surface. Gases are compressible to small fractions of their initial volumes. Because of this, large amounts of oxygen can be stored in tanks for scuba diving. Gases mix readily by diffusion. We don't have to stir or shake them to make them mix. Gases can escape containers through tiny holes in a process called effusion. This occurs when a bicycle tire is punctured.
Okay, now the kinetic molecular theory actually only applies to ideal gases. However, as I said before, many gases behave nearly like ideal gases if the pressure is not very high, in other words, at low pressures, and if the temperature is not very low. So at low temperatures and relatively high pressure, at low pressure and high temperature, the gases behave like an ideal gas. And so our description of an ideal gas is fairly good for most gases over most of the range of temperatures with which we are familiar. Okay, some of the properties of gases. Expansion. Gases do not have a definite shape or a definite volume. They expand to fill the container that they're in, and they will take the shape of the container. The gas particles move rapidly in all directions. That's assumption 3. Without significant attraction between them. That's assumption 4. Fluidity. Because there are no attractive forces between the gas molecules, they can glide past each other easily. That means that they can flow, and this makes them a fluid. Gases actually are fluids. We usually think of things like water and milk as being fluids, but gases are actually fluids also because they flow. Pressure, and now you'll see we're into chapter 11. So here we're really starting on chapter 11. Pressure is defined as the force per unit area on a surface. Gas pressure is caused by collisions between the gas molecules and the surface of the container. And actually, a good model of this, I like to use the idea of students in a room. Consider a class full of students. Take all the furniture, all the fixtures out of a room. So you just have a room with walls. And put a bunch of students in there, blindfold them, and tell them, walk. Okay? As they're walking around, they're going to bump into and bounce off of each other. When they hit the wall, they will bounce off of the walls. And the number of collisions that the students make per unit of time, per unit area of wall, determines the pressure. If I were to tell the students, okay, run, so now they're running through the room. Again, they're still blindfolded. They're bouncing off each other, but you're going to have more collisions with the wall. This would represent a higher pressure. So what that shows us is that as you increase the temperature of a gas, you will increase the pressure if the volume remains the same. Okay, so and this kind of brings that all together. The pressure exerted by a gas depends on volume, temperature, and the number of molecules present. The greater the number of collisions of gas molecules, the higher the pressure will be. The collisions between the gas molecules and the wall. The greater that number is, the higher the pressure.
Pressure is caused by the collisions of gas particles with the side of the container. With a large volume, the particles do not collide with the sides of the container very often, and the pressure is relatively low. When the volume decreases, the particles of the gas collide with the sides of the container more often. With more collisions, the pressure increases. Boyle's law states that the volume of a fixed mass of gas varies inversely with pressure at constant temperature. In other words, the smaller the volume, the higher the pressure.
Okay, now this is a really good one, so you got to watch this carefully.
Pressure equals force over area. 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 Pressure equals force over area.
Oh, excuse me, what's that? You want to hear that again? Okay, let me play it again.
Pressure equals force over area.
Okay, this is just the equation for pressure. It's force per unit area. Okay, so it's
pressure equals force over area.
There you go. Wasn't that interesting? Okay, the SI unit for force is the Newton, and that's the force that will increase the speed of a 1 kilogram mass by 1 meter per second squared. Okay, 1 meter per second per second. It is not actually a really large force. If you have a person on the surface of the earth that has a mass of 51 kilograms, and notice that this is correctly stated here, the mass of the person is 51 kilograms. At the surface of the earth, the acceleration due to gravity is 9.81, or here they say 9.8 meters per second squared. The force exerted by that person on the ground, therefore, would be 51 kilograms times 9.8 meters per second squared, which gives you 500 kilogram meters per second squared, which is a Newton. Okay, a kilogram meter per second squared is a Newton, so that's 500 newtons. That's the force they're applying to the ground. So if that person is standing on the floor and their feet, the part of their feet that is in contact with the floor, has an area of 325 square centimeters. The pressure would be 500 newtons divided by 325 square centimeters is 1.5 newtons per square centimeter. The greater the force on a given area, the greater the pressure. If that was a 102 kilogram person, you would have twice the pressure. You would have pressure. They would then weigh. Their weight would be 1,000 newtons divided by 325 square centimeters would be 3.0 newtons per square centimeter. The smaller the area on which the force acts, the greater the pressure. Okay, so you can, if you want to increase pressure, you can either increase the force or you can decrease the area over which that force acts. And here you see that relationship. Here you see a person standing on the floor. This is our 51 kilogram ballerina. When both of her feet are in contact with the floor, she is applying her weight over an area of 325 square centimeters for a pressure of 1.5 newtons per square centimeter. When she gets up onto both tiptoes, her area is decreased to 13 square centimeters, so the pressure is 38 newtons per square centimeter. And then when she lifts that 1 foot, so she's just on one set of toes, now the pressure goes to 77 newtons per square centimeter. So by decreasing the area over which the same force acts, you increase the pressure. The barometer is the device that's used to measure pressure, and this was invented by Evangelista Torricelli. He's an Italian. He invented this in the early 1600s. He noticed that water pumps could only get water to a height of 34 feet. They would not be able to raise it higher than that. He wondered about that and thought that it must depend somehow on the weight of the water compared to the weight of the air. And so he reasoned that if he used mercury instead of water, it would give him a column that would be more easily measured. Instead of having to measure the height of a column 34 meters, he could measure 1/14 of that. And so he sealed a glass tube, one end, filled it with mercury, and inverted that tube into a dish of mercury. This was at a time when people didn't know that mercury was toxic, and he was okay playing with it. We can't do this now. We're not even allowed to have mercury in our building now. But at his time, he found that the mercury rose to about 30 inches, or 760 millimeters, which is about 1/14 of 34 feet. Here you see a picture of a barometer. It's a sealed glass tube filled with mercury, and then that's inverted into a dish of mercury. I'll play this so you can see how this works.
A barometer is a device for measuring atmospheric pressure. The simplest type of barometer uses a transparent tube, usually glass, which is sealed at the top and filled with mercury. The tube is inverted in a bowl of mercury. When the air pressure is high, the mercury is pushed up the tube. When the air pressure is low, the mercury is lower in the tube.
Okay, so you can see that as the air pressure increases, you have more force pushing down on the surface of the mercury here, and that's transmitted up here to a higher level of mercury in here. So by measuring the difference between the level of mercury in the dish and the level of mercury in the column, you have a means of measuring pressure. And this leads us to our most common unit of pressure, and that's the millimeter of mercury. And we symbolize that here, mmHg, millimeters of mercury. That pressure, 1 millimeter of mercury, is also called a torr in honor of Torricelli. So a millimeter of mercury and a torr are exactly the same thing. We can also measure pressure in units of atmospheres. And this is because the standard atmospheric pressure, or the average atmospheric pressure at sea level at 0 degrees Celsius is 760 millimeters of mercury. That's defined as 1 atmosphere. In the SI system, pressure is expressed in pascals. A pascal is defined as a force of 1 Newton per square meter. Now, remember we said a Newton is not a particularly large force, and a square meter is a fairly large area. So a pascal is a kind of a small unit of pressure. And this, by the way, was named after Blaise Pascal, who was a mathematician. But because the pascal is so small, we often use kilopascals as a unit of measure. And in this case, 1 atmosphere is equal to 101.325 kilopascals. And so here you see a chart. This chart is also in your book, but it tells you that the different units, how those units are defined, and you can see each of the units that we commonly use is shown here. And these are the ones with which you should be familiar. You don't have to memorize these definitions, but you should be familiar so that when you see torr, you know that that's a unit of pressure, or pascals, or kilopascals. You're aware that these are units of pressure and that that's what we're measuring. All right, here's the sample problem. In this case, we're asked to convert atmospheric pressure. It says the atmospheric pressure in Denver, Colorado is 0.830 atmospheres. Now, you would expect Denver to be a little less than 1 atmosphere because they're above sea level, about a mile up, and so the pressure is a little bit less. And so they're at 0.830 atmospheres. It says express that in millimeters of mercury and in kilopascals. This is a fairly easy problem to work. Let me get my pen set here. Okay, first of all, we'll start with the number they give us, 0.830 atmospheres. We need to multiply this by a fraction that has atmospheres on the bottom and millimeters of mercury on the top. Okay, and so our conversion here is 1 atmosphere is equal to exactly 760 millimeters of mercury. Now that's an exact number, so we're not concerned with sig figs there. So if we just do the multiplication here, we have 0.830 times 760, and this will be to 3 sig figs. I get 630.8, so we would round that to 631 millimeters of mercury. Okay, so that's our first answer. The second one is done in a very similar manner. We have 0.830 atmospheres, and in this case we're going to multiply by the 1 atmosphere and kilopascals, and there are 101.325 kilopascals in 1 atmosphere. And again, now it's just a matter of arithmetic. 0.830 times 101.325, and I get 84.099. So again, 3 sig figs, 84.1 kilopascals. Okay, and now let's just take a quick look at their solution. And there's the planning, how they're going to solve it. And you see that's very much the way we did. Millimeters of mercury over atmospheres, kilopascals per atmosphere. And so now plug the numbers in, and they get the same two answers that we got. Okay, so we did that one okay. Okay, finally, Dalton's law of partial pressures. The law of partial pressures tells us that in a mixture of gases, each individual gas contributes something to the total pressure of that gas. This was discovered by John Dalton. He's the one that gave us the atomic theory, and he was the one that proposed this or discovered this idea. And it's important to us because of the way we often collect gas in the laboratory, which is we collect it by displacement of water. And so the gas will always pick up some water vapor in it. And so if we want to know what the pressure of the gas is, we have to be able to calculate that. Okay, and so we see here that the total pressure of a gas mixture is the sum of the partial pressure of each of the gases that's in it. So for example, in the atmosphere we have nitrogen, which produces a partial pressure, oxygen, which produces some pressure, and then we have small amounts of water vapor and carbon dioxide and argon and all the other gases that are in the atmosphere. Each of those contributes something to the total pressure.
Dalton's law states that the sum of the partial pressures of individual gases in a mixture equals the total pressure of the mixture. For example, in this container, we can measure a pressure exerted by the oxygen in the container. If we begin to add nitrogen to the mixture, the pressure begins to rise. When the addition of nitrogen is complete, the partial pressure from the nitrogen plus the partial pressure from the oxygen equals the total pressure of the system. In a mixture of gases, the total pressure of the mixture is equal to the sum of the pressures of each individual gas alone.
Okay, I don't think we need to spend any more time on that. Okay, and so as I said, we normally collect gas in the laboratory by displacement of water, and so there is water vapor in the gas that gets collected. And so we very often have to do a calculation to figure out what is the pressure of just the dry gas that we have in there. If we want to calculate amounts of gas and so on, we need the pressure of the dry gas. And so you will need to look up the vapor pressure of water, and this of course depends upon the temperature at which you're carrying out your experiment. If you open your books up to page 859, you will see at the page a chart that gives you the partial pressure of water at various temperatures. And so we'll take a look at how you use that chart. If you're going to find the pressure of gas inside of a bottle, you're going to use this equation. The partial pressure, or the atmospheric pressure, is equal to the partial pressure of the gas plus the pressure of the water vapor for the temperature that your experiment is at. Now, and this actually is not the form that you're going to use it, because you're going to take the atmospheric pressure and subtract the partial pressure of water vapor to get the pressure of the gas in the container. And that's the one we want to solve for. So it's actually, we should write this as P sub ATM minus pH sub H2O equals P sub gas. Now, before you do this, you have to make sure that the water levels inside and outside the bottle are the same. That way you're certain that the pressure, the total pressure inside the bottle and outside are the same. If there's any difference in those water levels, then there would be a difference in the pressure. So you have to make sure that it's the same both inside and outside. The atmospheric pressure you can get from a barometer, and as I said, the value for the partial pressure of water vapor can be found on page 859 in your textbook. This shows you an example of how gas is collected. What you see here is this is a Thistle funnel, It goes down into this jar, or this flask, which has some zinc on the bottom. When you put sulfuric acid in here, that comes down and it reacts with the zinc, forming hydrogen gas. Hydrogen gas is given off, passes through this tube here, and it bubbles up into the collection jar here. And so we're collecting the hydrogen gas up here, but because it's bubbling up through the water and we have a water surface in there, this is going to be saturated with water. And so we need to know what is the partial pressure of water at the temperature that this collection is going on at. Okay, and that's the reason why we have to do that. Okay, so let's take a look at a sample problem here. We have oxygen that's collected from decomposition of potassium chlorate. The barometric pressure and the temperature during the experiment were 731 torrs. And remember, 1 torr is equal to 1 millimeter of mercury, so we can just call that 731 millimeters of mercury, and 20 degrees Celsius, respectively. What was the partial pressure of the oxygen collected? Okay, well, if we take our original equation, P sub ATM equals P sub gas plus P sub H2O. We can rearrange this. P sub gas is equal to P sub ATM minus P sub H2O. All right, so it tells us that the atmospheric pressure here is 731 torrs. So we can start, and I'll just rewrite this, P sub gas is equal to 731.0 millimeters of mercury minus, and then we have to go to our book and find the partial pressure of water at 20 degrees Celsius. And at 20.0, that partial pressure is 17.5 millimeters of mercury. So we subtract 17.5 millimeters, and we get the partial pressure of the gas, or the pressure of the gas, just by doing that arithmetic. 731.0 minus 17.5, and we get 713.5 millimeters of mercury. So that would be the partial, or the pressure of the dry oxygen gas. And we'll take a look quickly here at their solution. Here they've written the equation, changed it, just like we did. And there's the answer, 713.5. Oh, I left mine in millimeters of mercury. They kept theirs in torrs. And again, those are interchangeable. So we got the right answer. And that's the end of this section. Sorry this was such a long one, but we had a lot of stuff to cover. Thank you.